Special Relativity Theory Part 4.3. Why does the length of a rod appear different from its real length? Lorentz transformation, length contraction and time dilation. As I mentioned in previous sections, the Lorentz transformation is the core of Einstein's special theory of relativity. It is supposed to translate the quantities of time and space between two inertial systems, and according to him, time dilation and length contraction are the results of Lorentz transformation. I have already presented some obvious contradictions to this theory and introduced a new and more understandable approach to deriving of the Lorentz transformation in Part 4.2. In this part I'd show why does the length of a rod appear different from its real length and why the Lorentz transformation is not the right means to calculate length contraction and time dilation, and the fact that all of these phenomena can be calculated and interpreted by Newtonian physics. Why does the viewed length of a rod appear different from its real length? Consider Figure 1 above. It shows two inertial systems K and K' with the relative velocity v. According to the observer on K, K' is moving to the right, and according to the observer on K', K is moving to the left. Assume a point P on the x-axis at a given distance from origin of K, O, P equals D. The same is assumed for P' on the x'-axis, O' P' equals D. So, at the moment t equals 0, when O and O' overlap, P and P' overlap too. This means that the real distance of P' from O and the real distance of P from O' are necessarily equal and both equal to D, contrary to Einstein's claim of the contraction of the real length, which obviously leads to contradiction. Of course, as long as K and K' are stationary relative to each other, the two observers would see P and P' overlapping. But it would be different if K and K' move relative to each other. For a better analysis, we distinguish between two cases, i.e. the case when K and K' move away from each other and the case when they move closer to one another. Case 1. The point P' moves away from the observer on K. If K' is moving to the right with velocity v relative to K at t equals 0, the observer in K wouldn't see the point P' at distance d from O, but somewhat closer to O, say, at distance d' smaller than d, so that d' plus v multiplied by d' over c equals d. Because the image of the point P' needs the transmission time, d' over c, to reach the observer at point O, and in this time span, the point P' moves an additional distance equal to v multiplied by d' over c away from him. So if at t equals 0 its real distance from K is d, the observer will see it at distance d', so that d' plus v multiplied by d' over c equals d, or d equals d' times a, where a equals 1 plus v over c. If we present d', the seen distance of P' from K, at t equals 0, with x sub s, and the real distance of P' from the origin of K at t equals 0, with x', we can write equation 13 x' equals x sub s multiplied by the quantity 1 plus v over c. Case 2. The point P' moves closer to the observer on K. Similar to the previous argument, if K' is moving to the left with the velocity v relative to K, the observer in K wouldn't see the point P' at its real distance, d, from O, at t' equals 0, but somewhat farther from O, say at distance d' greater than d, at t equals 0, so that d prime minus v times d prime over c equals d. Because the image of point p prime needs the transmission time d prime over c to reach the observer at point O, and in this time span, the point p prime moves an additional distance equal to v times d prime over c closer to him. So, if its real distance at t equals 0 from k is d, the observer will see it at distance d prime, so that d prime minus v times d prime over c equals d, or d equals d prime multiplied by a prime, where a prime equals 1 minus v over c. If we present d prime, the seen distance of p prime from k at t equals 0 with x sub s, and the real distance of p prime from the origin of k at t equals 0 with x prime, we can write equation 14 x prime equals x sub s multiplied by the quantity 1 minus v over c. Thus we could show that the so-called length contraction and consequently time dilation are simply physical phenomena which can be explained by the required transmission time of the image of the moving object to the observer. An observer would see the point P closer to himself if P is moving away from him. Equation 13. X sub s equals x over a, where a equals 1 plus v over c, a greater than 1, an observer would see the point P farther from himself if P is moving towards him. Equation 14. X sub s equals x over a prime, where a prime equals 1 minus v over c, a prime smaller than 1. And because time corresponds to distance. In the first case, t sub s equals x sub s over v, or t sub s equals x divided by a times v, and in the second case t sub s equals x sub s over v, or t sub s equals x divided by a prime times v, so the length L of a rod would be seen L prime equals L over a, or L prime equals L over a prime, if we have the case 1 or the case 2. Conclusion: the lengths of objects in the direction of movement are perceived differently than their actual length by the stationary observer. As an example, we assume an object of 10-meter length moving with the velocity v equals c over 2 relative to the observer in the origin of k. At t equals 0, one end of the object, x sub 1, is located at the origin of k. First question: where is the object relative to k after 100 seconds? X equals v times t equals 100 c over 2 equals 50 c, so x sub 1 equals 50 c, x sub 2 equals 50 c plus 10, the real distance of the beginning and the end of the object after 100 seconds. Second question: at which distance does the observer see the ends of the moving object, and what is the seen length of it after 100 seconds? If the observer sees the beginning of the object at distance d prime sub 1 from himself after 100 seconds, it means d prime sub 1 plus v times d prime sub 1 over c equals 50 times c, or d prime sub 1 multiplied by the quantity 1 plus v over c equals 50 c. So, d prime sub 1 multiplied by 1 plus 1 over 2 equals 50 c, and d prime sub 1 equals 100 c over 3. The view distance of the beginning of the object. d prime sub 2 plus v times d prime sub 2 over c equals 50 times c plus 10. Or d prime sub 2 multiplied by the quantity 1 plus v over c equals 50 c plus 10. So, d prime sub 2 multiplied by 1 plus 1 over 2 equals 50 c plus 10. And d prime sub 2 equals 100 c over 3 plus 20 over 3. The viewed distance of the end of the object from the origin of K. Third question, what is the viewed length of the object? L prime equals d prime sub 2 minus d prime sub 1 equals 20 over 3. Or we could simply use equation 15 L prime equals L over A equals 1 plus V over C equals 3 over 2. And obtain the viewed length of the object L prime equals L over A equals 10 divided by 3 over 2 equals 20 over 3 meter. And at last, contrary to Einstein, we didn't need to leave common sense aside. To be continued. Special relativity theory. Part 4.4. Introducing an alternative to the Lorentz transformation.